Hi everyone, I'm Hu Yang from National Taiwan University, and I will be presenting a bio-active Bi-Olfactory display using subwoofers for virtual reality. aBio is an active Bi-Olfactory display system that delivers scents to specific location. It provides users with a natural olfactory experience in free air by colliding two vortex rings launched from two subwoofer-based vortex generators. In 1962, Helen proposed Sensorama, a multisensory system that combined the human sense of sight, hearing, touch, and smell. He also suggests that including olfactory display in virtual reality would greatly enhance user immersion. There have been many olfactory displays proposed in recent years. One of the most typical types is environmental olfactory displays that usually use wind to spread odors throughout the space, such as Figure 2, which comes to the difficulty of positioning odors at a specific location. To break through this limitation, some researchers have also developed devices such as Figure 3, which use ultrasonic waves to control the diffusion of the odors. However, such methods require a large amount of odor diffusion into space, which cause scents to linger in the air. To solve this problem, wearable olfactory displays have been developed which deliver the scent directly to the user's nose, as shown in Figure 4, 5, and 6. However, the user must wear an additional olfactory device which reduces the user's immersion and comfort. Based on the limitations of the above two approaches, Yanagida proposed the method to deliver odor using vortex rings, and he developed a piston-driven vortex generator shown in Figure 1. This device delivers the scented vortex ring to user by the compression of the piston, which achieves precisely control of the odor without requiring the user to wear additional device. In order to reduce the haptic sensation caused by the vortex ring, Nakazumi proposed the method to collide two vortex rings in front of the users to provide a natural olfactory experience. Then, Murai added the depth camera to the system to allow the device to track the working user. As shown in Figure 4, Tomono have also tried to use this approach in LED screen olfactory display. Recent studies have shown that using vortex ring to deliver odor is a promising method, but I found no research has yet developed a vortex-based olfactory display based on the current immersive VR system. Also, most of the vortex-based olfactory display use large piston to compress the air, but I think the acoustically driven type vortex generator has a great potential for multimedia applications. For example, it can be developed a sound system capable of the precisely olfactory display, which can provide users with a multi-sensory experience. So, we present aBio, an olfactory display system based on two subwoofers-driven vortex generators. We also integrate the system with immersive VR, enabling the user to experience real-time interactive olfactory experience in the virtual environment. Next, I will introduce the unit of our olfactory display. It is composed of two parts, a scent generator and a vortex generator with a 2-dot platform. Most of the components are made by 3D printing. The method of the scent generator is based on Bernoulli's principle, as shown in the diagram on the bottom right. The air pump changes the air pressure in the container to pump the odor solution into the automation device. This device turns the solution into tiny droplets and delivers them to the chamber of the vortex generator. And the vortex generator can launch the scented vortex ring. It mainly consists of a subwoofer, a chamber, and a nozzle with a shutter. The figure shows the workflow of the olfactory display unit. First, the scent generators transmit the odor droplet into the chamber. Then the shutter opens, followed by a rapid vibrate of the subwoofer to push the air out of the nozzle, forming a vortex ring which carries the odor droplets to the target location. The shutter can lock the scents in the chamber when it is closed. To generate accurate and high odor concentration vortex ring, We have conducted a series of experiments during the development of our olfactory display unit. Due to the time limit, I will briefly introduce them in my presentation. If you want to see the detailed experiments, please refer to our paper. First, we conducted an experiment to find the best aperture. Based on the vortex formation, we simply printed 9 types of apertures. Since it is difficult to find a detection device that can sense arbitrary odor molecules, we used echo instead. And we built an electronic nose device that consists of 9 MQ3 sensors, which can evaluate the accuracy and the relative odor concentration carried by the vortex ring. The results show that the aperture with a 29 cm diameter and a 30 cm length provided the most efficient and accuracy scented vortex ring. We further conducted an experiment to find the best input signal waveform that can generate the scented vortex ring with high accuracy, odor concentration, and minimal noise. It should be mentioned that after testing, the power of wave without gain is not enough to produce vortex rings, and we get 6 dB as the minimum gain value. We finally tested 4 kinds of waves with 6 dB gain, and the duration ranges from 50 milliseconds to 110 milliseconds. The results show that clip sign, sync, and sync with heavy window pole signals has all effective in reducing noise, and they can reach 100% accuracy in the duration of 60 milliseconds and below. Since accuracy and minimal noise are our primary concerns, we decided to use the 60 millisecond clip sync with heavy window waveform. After figuring out the best hardware and software parameter of the olfactory display unit, we conducted an experiment to model the vortex ring movement more accurately. We used the image processing to analyze the trajectory of the vortex ring. Finally, we use regression to calculate the vortex time distance formula and graph. Next, I will introduce our Bi-Olfactory display system. The main concept of the system is to deliver the odor to a specific target point via collision of 2 vortex rings. And the demo video on the left side shows 2 vortex rings collided in front of the user's nose. The left side shows the system architecture diagram. We built the VR system on Unity, in which we set up an interface script to control our external devices, such as the subwoofer and the air pump. We also combine aBio with vibe tracking technology. Using the vibe tracker fixed on the vortex generator, we can calculate its rotation and position in relation to the user's nose or hand for real-time tracking. Through this approach, aBio greatly improves the spatial control of smell and makes it possible for the user to experience interactive olfactory experience without equipping additional device. Based on the biosystem, we conducted an experiment to evaluate the system's collision accuracy. We first preset 5 collision points as shown in the left figure. We controlled 2 olfactory display units to launch the vortex ring with smoke at these target points. Then we recorded the state of the vortex ring by high-speed camera. According to the right figure, there are 3 cases. We only consider the first case as a successful collision. At each point, we will repeat the launch 50 times to calculate the successful collision rate. The video on the left is the record of the collision experiment at point A and D. It should be mentioned that in unequal distance condition, we control the time difference between the 2 vortex ring launches to make them reach the collision target at the same time. This time difference is calculated based on the vortex ring movement model. The results show that the accuracy at 5 points are all higher than 80%. We also conducted a pilot study and a user study. The goal of the pilot study is to find the optimal field duration of the scent generator that can provide users with a maximum chance of smelling noticeable or strong smell. Also, we want to verify whether users can distinguish the intensity of the smell under different field duration. We first set the field duration at a range between 0 to 2 seconds, with 0.5 seconds as the interval. and the collision point distance was 5 cm from the area in front of the participant's nose. To enable participants to rate the perceived odor intensity, we defined 4 intensity levels. A total of 16 participants were tested. We first delivered 10 times scented vortex ring with 2-second field duration to the participants. We asked the participant to set the perceived intensity as strong to regularize the result. Then there are 5 rounds with 5 field duration. In each round, we delivered to them 10 times vortex ring with the same field duration. Finally, we asked them the score after each round. This is the result of the pilot study. The horizontal axis represents the field duration. The left side of the vertical axis represents the distribution of the participants. The right side represents the average score. And we created a black line using the average score. The results show that increasing field duration contributes to higher smell detection possibility. So we finally choose 2 seconds as our field duration to ensure that the user has the maximum chance of smelling noticeable or strong smell. Then we conducted a user study to determine the optimal collision distance that can provide the user with a high smell detection probability and weak haptic sensation. We tested the 6 collision distance under the 2-second field duration. It should be mentioned that many participants said it was difficult for them to assign scores representing the smell intensity during the pilot study. Therefore, we changed the scoring question to a true and false question. There are 3 questions, that is, if there was a smell, if the smell was too strong, and if there was a noticeable haptic sensation. To better understand the user experience, at the end of the experiment, we asked participants to fill in a questionnaire with 4 questions. A total of 12 participants were tested in the user study. The right figure shows the procedure of the experiment. Each collision distance was tested 10 times with 10 force launch, as well to determine whether this participant is an outlier. In each test, a virtual flower floated toward participants, accompanied by voice to guide them to inhale and exhale at the right time. If it was a true launch test, the system launched the vortex ring when the flower approached. We disrupted the order of these 120 tests and asked the question after each launch. This is the result of the user study. The horizontal axis represents the probability that participants feel the obvious haptic sensation, and the vertical axis represents the smell detection rate and the thickness rate. The results show that the best collision distance is between 12.5 cm and 15 cm, because in this range, there is about 80% chance that the participant can detect the smell, and only about 20% chance to feel the noticeable haptic sensation or a too strong odor. In summary, we proposed an active bi-olfactory display system that achieved precisely control of odor both in time and location. And we conducted several experiments deriving equation and optimal parameter based on the subwoofer-driven vortex generator, which can provide valuable reference for future developers. We also integrate the system with immersive VR, achieving real-time interacting olfactory experience in the virtual environment. And finally, we conducted a pilot study and user studies to find the correlation between import design configuration and human sense. In the future work, we would like to enabling the system to switch between odors in a short interval of time. We also want to extend the bio by adding more vortex generators to create an Bi-Olfactory display system with no blind spots. And with the advantage of the speaker, we believe it is possible to design a sound system capable of the olfactory display, which can provide the user with a multi-sensory experience.